Hi, my name is Tom Heffel, and this channel is all about helping students learn chemistry. In this video, we're going to learn how to calculate pH of strong acids and bases. And we're going to do three problems. The first problem is going to be a strong acid. The second problem is going to be a strong base with one hydroxide ion. And then the third problem is going to be a strong base with two hydroxide ions. And we're going to learn how to calculate the pH, but maybe just more than the pH. We might go back and review our topics on how to calculate pOH, concentration of protons, and concentration of hydroxide ions that we learned from the previous video. Okay, so let's get right into the first problem where we might have a substance in a beaker, okay, and in the beaker we have 0.1 molar hydrochloric acid. And the first thing that we need to do is identify hydrochloric acid as a strong acid, because it's going to behave one way, which is going to be different than the way we handle weak acids, which is the topic of our next video. But hydrochloric acid is a strong acid, so that means it gets the single arrow. That means all the reactants are going to push over to products, okay, and this thing's going to split up into its ions. Okay, now when we have a single arrow, as a teacher, I like to use something called a BCA. Okay, and the B stands, well, what is it before? And then there's going to be a change, and then what is it going to be after? Other instructors might call this an ICF, initial, change, final, okay? And both of them are perfectly acceptable. I just like to use the BCA for single arrows, okay? And what I know is that our concentration of the hydrochloric acid is 0.1 at the very beginning, okay? We don't have any of those products, but what's going to happen is everything's going to shift to the right because this is a single arrow. So in the end, I better have 0% of hydrochloric acid and 100% of the ions, okay? So this is going to go down 0.1, leaving nothing left over, okay? And if this goes down 0.1, then this is going to go up 0.1, this is going to go up 0.1, so this is 0.1, and this is 0.1, okay? Now, the part that I'm most interested in is this concentration of the protons. Concentration of the protons is 0.100, and from our previous video, if we have one of these, then we can figure out all three of them by using some of these equations, okay? Now, the first thing that I'm going to do is I'm going to figure out the concentration. Well, let's go ahead and calculate the pH, because that's the title of the video. So we will go from here to here first by using this equation. The negative log of the concentration of protons is the pH. So I'm going to rewrite that equation. pH is the negative log of the concentration of the protons, and the concentration of my protons is 0.100. So I'm going to go ahead and plug that into my calculator. The negative log of 0.10 ends up being 1.00 for the pH. So now I have the pH, okay? The next thing I'm going to do, I'll come back here, and if I have the concentration of protons, then I should be able to calculate the concentration of the hydroxide ions by using this Kw expression. And Kw is 1.0 times 10 to the negative 14, and that's equal to the concentration of the protons, which I just got from right here. So 0.100 is the concentration of the protons, and therefore I should be able to figure out the concentration of the hydroxide ions. And what I'm going to do is I'm going to divide by 0.1 on both sides. So the concentration of my hydroxide ions ends up becoming 1.0 times 10 to the negative 13. So now I have that value as well. Okay, so I kind of went from here to, oops, wrong spot. Okay, should be down here, 1.0 times 10 to the negative 13. I use this number to kind of get here. And then I'm going to use this to get to the pOH, because the pOH is the negative log of the concentration of hydroxide ions. So pOH is going to be the negative log of the concentration of hydroxide ions. And if I plug this into my calculator, it equals 13, okay? 13.00. Of course, as our check, pH plus POH, if I add these two things together, it should equal 14. It does, and I've done everything correctly. Okay, so quick review. Okay, I took my 0.1 molar of hydrochloric acid and used this chart called a BCA to figure out the concentration of protons. I use that concentration of protons to calculate pH. I use the concentration of the protons to figure out the concentration of hydroxide ions. And then I use the concentration of the hydroxide ions to calculate the pOH. And we're just going to repeat that 2 more times, but instead of a strong acid, we're going to do a strong base with 1 hydroxide ion or 2 hydroxide ions. So let's go ahead and erase this work here, okay, and move on to that second problem. Now, the second problem is situated something like this, okay? I got this beaker, okay, and there's 100 milliliters in it, and I'm going to put in 3.50 grams of sodium hydroxide. So all I'm doing in this problem is disguising the pH and the pOH and the other variables a little bit more by giving you these givens, okay? The first thing that I need to do is to calculate the molarity of the sodium hydroxide. I need to know the concentration of the acid because in the last problem, that's kind of what I started with, the concentration of the acid. So let's go ahead and calculate the concentration of the sodium hydroxide. Now to calculate concentration, remember, it's the moles over the volume in liters. So I got to convert these grams into moles, and there are 40 grams per 1 mole of sodium hydroxide. So when I add up 1 sodium, 1 oxygen, 1 hydrogen from the periodic table, I get 40. And 3.5, okay, divided by 40 is going to give me the answer of 0.0875 moles, okay? Now, I got to divide that by the volume to get the molarity. The volume here is 100 milliliters, but this volume has to be in liters. So if I convert that over to liters, it ends up being 0.100 liters, and I find out that my molarity is 0.875 for the molarity of the sodium hydroxide, okay? Now, I'm going to do the same thing that I did in the last problem. Is I'm going to start out with an equation for a strong base, okay? So if this is a strong base, it's going to ionize 100%. It's going to dissociate or break up into its ions of sodium and hydroxide. And I'm going to use that BCA again, and I'm going to plug in 0.875 right here. And I know that 0.875 is going to shift all the way to the right, okay? Because this is a strong acid, we have to use that single arrow, and everything pushes over to the right-hand side. So there's not going to be anything remaining over here. So this is going to go down by 0.875, so there's nothing left. And if this goes down by 0.875, this goes up by that same amount for both of them because it's a 1-to-1-to-1 ratio. Okay, so this ends up being 0.875 and this ends up being 0.875. And the interesting piece here, this time because it's a base, I'm ending up with the hydroxide ion concentration. So the hydroxide ion concentration is going to be 0.875. And once again, if I know one of them, then I can figure out the other 3. Okay, the first one I'm going to go ahead and figure out is the concentration of the protons by using my Kw expression. Kw is equal to 1.0 times 10 to the negative 14, and that's equal to the concentration of the protons, which I don't know, times the concentration of the hydroxide ions, which I do know, as 0.875. So I'm going to divide by 0.875 on both sides, and that's going to give me the concentration of the protons as being equal to 1.14 times 10 to the negative 14. Okay, so the concentration of the protons is 1.14 times 10 to the negative 14. And what I'm going to do is I'm going to take the negative log of that to figure out the pH, because the pH is the negative log of the concentration of the protons. And if I have the concentration of protons, I'm going to plug them right in there, and I find out that this ends up with a pH of 13.94. I'm going to do the same thing, so that's 13.94. And then I'll do the same thing for the POH. That's the negative log of the concentration of hydroxide ions. So I'm going to take this value of hydroxide ions and plug it in there. And I find out that this has a POH of 0.058. Okay, 0.058. Okay. And then when I add these two things together, does it get close to that number of 14? Absolutely. Just a little bit of rounding error. And I feel really good about all of these calculations. So the pH, which is kind of a title, calculating the pH of a strong acid or base, okay, is 13.94. And just as a quick recap, I converted the grams into moles, divided by the volume to get the molarity, or the concentration of the sodium hydroxide. I plugged that into my BCA and everything pushed over to the right-hand side, and the item of interest was the hydroxide ion. And as soon as I had that hydroxide ion, I could figure out the other four. Okay, so let's go into that last problem and see how it's just a little bit different than this previous problem that we just finished. Okay, so I'm going to set all of this up, do some quick erasing. And the last problem is going to be, instead of 3.5 grams of sodium hydroxide, what if we had 3.5 grams of strontium hydroxide? Well, a lot of this problem is the same, okay, with one exception, okay? So it's going to start it out exactly the same way. We're going to convert the grams into moles. Now, when we do that, there's a lot to add here. We got 1 strontium, 2 oxygen, and 2 hydrogens. And if you add all that together, it comes out to 121.6 grams for every 1 mole, okay? And then so when I take 3.5 and I divide it by 121.6, okay, I get a value of 0.0288 moles. Remember, I have to divide it by the volume in liters to get my molarity of 0.288 molarity of strontium hydroxide. Okay. Now, this is the part that is a little bit different. Okay. I'm going to take this strontium hydroxide and I'm going to write a good equation for it. And this equation, like I said, this is the part that's a little bit different. It's going to end up turning into strontium ions and 2 hydroxide ions, because there's 2 hydroxide ions present. Okay, so when I do my BCA, okay, and I plug in 0.288 here, all that's going to shift to the right. So all of this is going to be consumed. There's not going to be anything left over whatsoever. And this is going to go up 0.288 because of the 1-to-1 ratio. But this is not going to go up 0.288 because it's a 1-to-2 ratio. Remember, for every 1 strontium ion that I get, I'm getting double the amount of hydroxide ions. So the hydroxide ions have to be twice as concentrated as the strontium ions. And that number is going to come out to be 0.576. So if I double this, it equals 0.576. And it's that 0.576 number that I'm really interested in, because if this is the concentration of the hydroxide ions, then I just finished the problem the same way I did the other two. And that's by using the Kw equation, which is 1.0 times 10 to the negative 14 is equal to the concentration of protons times the concentration of hydroxide ions. And that's coming out to 0.576, okay? So I'm going to divide by 0.576 on both sides, and that will give me the concentration of protons. Concentration of protons ends up being 1.74 times 10 to the negative 14. So if I have that value of 1.74 times 10 to the negative 14, I can use that to calculate the pH. Remember, pH is the negative log of the concentration of protons. So I'm going to take that value and plug it in right here, and I end up finding out that this thing has a pH equal to 13.76, which sounds like a pH for a strong base, okay? And then if I wanted to figure out the POH, I would take the negative log of the concentration of hydroxide ions, which is 0.576. And if I plug that in there, I get 0.24. So 13.76 for the pH. The pOH is 0.24. And finally, as my check, I'm going to add these two together to see if it equals 14. And it does. So I know that I've done all of my work correctly. So if you found this content helpful on how to calculate pH of strong acids and bases, please give it a like and subscribe. And when you add that comment, it really does push the information out to other students that are trying to learn chemistry.